Good morning. This is Tactical Generator Monitoring System for the EECS Capstone Group, and this is our Sprint 3 review. For our agenda today, we have our introduction followed by the product vision, then our sprint goal, then we'll move on to our team contribution, our recommendation, our goal assessment, and lastly, we'll move on to our product roadmap. For our electrical engineers, we have Cadet Anderson, Cadet Paringer, Cadet Stahl, Cadet Sun, and for our information technologists, we have Cadet Bondock and Cadet Munkter.
The Tactical Generator Monitoring System is a power monitoring device intended to save American lives. There are enemies inside the wire, and their names are wet stacking and overloading. Fuel must be brought to forward operating bases by ground vehicles in order to be cost efficient. This operation costs lives every year as insurgents plant improvised explosive devices and ambush caravans. Service men and women are fearing for their lives. This process can be reduced by using fuel and generators efficiently with our product. No country should allow deadly inefficiencies. Our vision is to create a product that can conserve fuel and prolong generator health in order to reduce the amount of dangerous caravans bringing fuel and generators to forward operating bases. Members of this project will lead these soldiers in a year. They are motivated to put out a quality, effective product, as it may be their soldiers that are put in danger. This product has been developed by multiple classes of electrical engineering majors, IT majors, electrical engineering Army officers, and United States Military Academy professors. It was also presented at the Army Research Lab in the fall by Cadet Anderson. Our plan is simple. The Tactical Generator Monitoring System team hopes to create a monitoring system for all Army microgrids in war zones around the world. These systems will flawlessly integrate in their microgrids, using a simple series connection between generators and loads. We promise to design the most robust, applicable product in our power. Please enjoy the progression of our project. The U.S. Army continues to be on the forefront of effective militaries. We will not waste taxpayer money and lives.
The goal for Sprint 3 is to set the conditions to prepare for the assembly phase of the prototype. For our capacity, our expected hours was 168 hours. Our actual hours was 180 hours, and our scope was 1.071.
This is Cadet Paringer. For Sprint 3, I finished the hardware design. I met with the product owner multiple times to find both the signal and current transformer that would meet our project specifications. After finding both parts, I sent them to Moses Sun, and they were ordered. I also created a current transformer test plan with a specific burden resistor, function generator, and potentiometer. Finally, we created a plan to optimize our project day presentation. We would like to have both valuable content and a fantastic board to attract spectators. This will start with a branding initiative. I created an elevator pitch for our project. I am working with an artist to create a simple logo that represents our project, and I'm also working with Dr. Duncan to understand the synergy of our project with a similar project at Army Research Lab. This is all to create a shared understanding of the value and necessity of this project that someone with little electrical engineering background can understand.
This is Cadet Stahl. In support of the Sprint 3 goal to set the conditions to prepare for the assembly phase of the prototype, this sprint, my focus was working with the other EEs on the wire diagram, making the voltage transformer test plan, and working on the C++ code for the A to D converter. We finished the wire diagram, and I finished the voltage transformer test plan. Both are posted on Trello. I need to work more with Ari, Christian, and Moses to finalize the C++ code for the A to D converter. Shown here is the voltage transformer that I developed the test plan for.
This is Cadet Anderson, and my goal for the sprint was to accomplish the following tasks: complete ordering the generator connectors, confirm the hardware design with the electrical engineers, develop a wiring diagram, develop a more refined roadmap, and complete the sprint video. I was generally successful in all of my goals for the sprint. I was able to finish ordering the connectors through Dr. Duncan and her connections at CERDEC. The connectors, except for one, were received on Tuesday. I was able to confirm the hardware design with the electrical engineers and develop a wiring diagram that would set us up for success when all of the parts are received in our prototyping phase. Finally, I successfully updated a refined roadmap that included more of our specific goals moving forward this semester, as well as some communication events in which we are looking forward to participating. I was unable to accomplish finishing the discrete Fourier transform code to implement into our code because the research was more involved than I thought. I plan to finish investigating the code and translating it into our uses for this project. This slide demonstrates the hardware design and wiring diagram I was able to create after consulting the electrical engineers. As you can see, each phase of the load is monitored with a current transformer and voltage transformer, and are used to find the potential difference relative to the neutral wire. The outputs of these devices will be wired to the inputs on the A to D converter, which is attached to the Raspberry Pi. The output to the A to D converter is where the discrete Fourier transform is integrated into the design. This slide demonstrates some of the research I was able to do with Cadet Sun. We both investigated different options for the Fourier transform and found a website that had an algorithm we thought was feasible to implement into our final design. Like I mentioned in my previous slide, the code still needs to be finalized. We need to determine a sampling rate of our discrete outputs and successfully convert the code into C++ so that we could include it in the coding algorithm that we are finalizing.
This is Cadet Sun. For Sprint 3, my main priority was to complete the ordering parts memo and transfer code from Arduino to Raspberry Pi. We ran into an obstacle in ordering parts where our selected current transformer was out of stock and our voltage transformer was too expensive and was not meeting our project goals. While we received the majority of our parts, such as the Raspberry Pi and its additional hardware and the generator connectors, we are currently waiting on the current and voltage transformers. Because of the pending parts, I was not able to complete the setup for the hardware design and to integrate the wiring diagram completed by Cadet Anderson. Next, I worked with Cadet Bondoc and Cadet Munkler to convert Lieutenant Madison Stark's Arduino code into a compatible language for the Raspberry Pi. We initially chose to convert the code into Python, but after running into issues with incompatible Arduino libraries and rewriting certain aspects of the code, we decided on two alternatives. Cadet Munkler and Cadet Bondoc will go into further detail for the two alternatives. But primarily, I'm working on the conversion to C++ because of its language structure being more compatible with the existing Arduino code. Coding in Python would take considerable more time due to rewriting of Arduino code to create object-oriented programming and rewriting Arduino libraries. Furthermore, this slide highlights the high-level diagram needed in our code integration. We will need to integrate a new algorithm for capturing a sampling window at 60 Hz from the sampled digital signal, a discrete Fourier transform algorithm for calculating the magnitude and phase, and lastly to integrate an algorithm to derive the real power, reactive power, and power factor. These three algorithms will then be displayed digitally in our UI.
This is Cadet Mukhtar, and during this sprint, I worked on running Arduino sketches on Raspberry Pi, converting Arduino sketches to C++, and making the video for the sprint review. In order to implement previous year's work, Cadet Bondoc, Cadet Moses, and I worked on converting the Arduino code to C++ in order to use it on Raspberry Pi. While doing some research, I found a way to run Arduino sketches on Raspberry Pi from the Arduino IDE. This Arduino framework for Raspberry Pi allows us to run Arduino sketches directly on Raspberry Pi using Arduino IDE and Arduino libraries. With some modifications of the Arduino IDE, we were able to run test Arduino sketches on Raspberry Pi. However, we might face problems when we try to implement the analog to digital converter on Raspberry Pi. In order to mitigate future problems, I'm working close with Cadet Dalton, who is in charge of analog to digital converter.
This is Cadet Bondoc. My main priority this sprint is to successfully convert Cadet Stark's code from Arduino implementation to Raspberry Pi implementation. We prioritize this specific task because the project is dependent on Cadet Stark's algorithm. The Arduino to Raspberry Pi implementation proved to be more difficult than expected. While Cadet Munkter worked on a way of using the Arduino IDE on the Raspberry Pi, Cadet Sun and myself worked on converting the code through C++. This involved researching C++ libraries and comparing them to the Arduino libraries that Cadet Stark used. While we were able to convert the code onto the Raspberry Pi, we were not able to test it due to the lack of parts. Also in this sprint, Cadet Sun and myself installed the AD converter and the touchscreen interface on the Raspberry Pi. Due to the priority of converting Cadet Stark's code, I was not able to make substantial improvement to the UI design.
Goal assessment. We mostly completed our sprint goal. At this time, we are not prepared to assemble the prototype, but we are extremely close with everything within our control. We have not received our parts. They are, however, ordered and on their way. We have not completed the Fourier transform signal sampling code. However, we have done preliminary research and it is being developed. We have converted Cadet Stark's monitoring algorithm to C++. However, we do not have the parts necessary to test that code. These failings are all correctable, and we have plans in place to remedy them in Sprint 4. Our parts are ordered, our code is almost ready with the exception of the Fourier transform and signal sampling code.
The proposed goal for Sprint 4 is we hope to test all parts and set the conditions to put our system together. As Cadet Perringer stated, we need to go back and finish some of our unfinished work from Sprint 3. Keys to success in Sprint 4 are testing the parts immediately as we get them, placing extra emphasis and time into the code. We will find code online and incorporate it into our code to save us some time there. Test the code as soon as we get the rest of the parts that we need, and we must begin final assembly of our parts and leave time for unexpected debugging.
This is our current roadmap for second semester. Updates include making the focus of each sprint more directed with deliverables for each sprint. The roadmap clearly shows when we plan to have the prototype completed and a functional product designed. Additionally, we plan to compete and attend the MIT Soldier Design Competition in the spring and added that to one of our communication events.